Okay, then our new lesson today, lesson 40, we're going to be reviewing the laws of logarithms that you learned and worked with last year. And we're also going to be talking about inverse functions. So as we get started here, let's go over a little bit of vocabulary. This is pretty much all review at this point. Remember, an argument is the input value. It's whatever we plug in. That's going to come into play as we talk about what inverse functions do to each other. I also want you to remember that logarithms are exponents. So when we derive our properties for logs, we're going to do that by thinking about how did our exponent properties work. We also need to remember that when we have logarithms, the base and the argument have to be positives, especially the argument. We're going to have to be checking that as we're solving some logarithmic equations. We also want to remember that inverse functions undo each other. So that means the composition both ways, f of g and g of f of x, both get us back to x. So what that is saying is if I take an input x, I put that into g and get an answer, and then I put that answer in and do whatever the f function says, it gets me back to the input that I originally started with. So f does something to it, g undoes that and gets it back to x. And it works the other way around as well. G of f of x is just x. The first inverse functions that we are going to talk about will be that logarithms and exponentials are inverses of each other. So this is a whole bunch of words saying that if I take some base and raise it to a log that has the same base, then whatever the argument is of the log in that exponent, that is going to be the value of that expression. In other words, b log b, like this, cancels out. That could be 10 to the log base 10 of x. 10 log 10 cancels, and we just have x. It could be 6 to the log base 6 of 24. 6 log 6 cancels, and we just have the 24. It could be e to the log base e of x, or that's what we call the natural log. E to the log base e will cancel out, and we just have x, because those are inverses and undo each other. That's one direction. We just saw f of g and g of f both have to get back to x, so this needs to also be true going the other way. And so going the other way, it becomes if a log with a base that is the same base as something with a power, then the value of that is the power. So the log can come first. Log base b of b cancels out, and we just have the exponent. We could have log base b, or log base 10 of 10 to the 5th. Log base 10 of 10 will cancel, and we'll just have 5. It could be log base 6 of 6 cancels to the 3rd, so we just have the 3 left, so that value is 3. Is that much making sense? So we're going to be using that as we simplify some log problems. We are also going to be using our log properties that we'll write in our formula page on the next slide. This slide I'm just going to talk about where they come from. Logs are exponents. So we know when we have exponents, x squared times x cubed is x to the 2 plus 3. So if we have a problem where we are adding exponents, we're adding logs, that means that the arguments had to be multiplied. And I'll write that out in log form in just a moment. We also know that if we divide x to the 5th over x to the 4th, that's when we subtract the exponents. So if we have a log minus a log, we're subtracting exponents, so we need to divide the arguments. And the last one, we know that the power, should be a times in between there, x cubed to the 6th is x cubed, or x to the 3 times 6. So if we have an exponent, so a log, that gets multiplied by a number, that means we took the argument to a power. So when we have those written out with logs instead of exponents, they look like this. If we have, and they go both ways, if we have a log plus a log and the base is the same, so we're adding the logs, we're adding the exponents, that happened when the arguments needed to be multiplied. Sometimes we will have log of something that we can factor, and we're going to want to break that down as the log of the first factor plus the log of the second factor. If we are subtracting two logs, that's like subtracting two exponents. That's when we were dividing arguments. If we have a log of a fraction, we may sometimes want to expand that as the log of the numerator minus the log of the denominator. And finally, if we have a power on the argument, we can bring that out in front. Or if we have a number out in front of the log, we can take that inside as an exponent on the argument. So now that you see these, do you remember that you had these last semester in the spring, but have probably forgotten it over the summer with not using it? That would be pretty normal. But hopefully it's at least like, yeah, I remember we saw stuff like that. And then we're going to do just a bunch of examples practicing using those in different ways to solve different exponential or different logarithmic equations. Just as soon as it looks like everybody's finished writing. Does anybody need me to wait? Okay, let's go on then to our first example. So I have log plus log on the left. It's nice, all of my bases, both sides are 80. I like it when I get the same base in problems. Which property can we use to simplify that left side a little bit? Who sees one of those that we can use on the left side? Look at the formula list. You can have that out. Which one of those is going to help us with this problem? Mia, what do you think? So we're adding logs, so that's like adding exponents. That happens when the arguments are multiplied. So we can take the 7 times 7. Now I have log equals log. What can I do whenever I have log with one base equals log with the same base? Allie? I can just set that the arguments are equal. So I can say that the 49 equals the 9 plus x. The reason I can do that is logs and exponentials are inverses. So if I have a log and I want to get rid of it, I can take the exponential of that. I can make that be an exponent of something that had the same base. So 80 to the log base 80. 80 to the log base 80. Do that on both sides, and those cancel out, so the arguments are equal. So then it is simply a matter of saying that x is 40. We have to check on every logarithmic problem, did we have a positive argument? So if x is 40, let's see, 7's always positive, 7's always positive, 9 plus 40 is positive, so we keep that. However, I want to caution you. You are not checking, is x positive or negative? Sometimes a positive x doesn't work. Sometimes a negative x does work. It all depends on the argument. If this had been 9 minus x, and somehow I still got 40, 9 minus 40 would be negative. So even though 40 was positive, the argument would have been negative and I'd have to throw it out. And my other caution is check it in the book, not the first line you might have written on your problem set paper. Because some of you do a first step mentally, and that might have been enough to make it work, whereas the original one, it would not work. Ready to try another one? Okay, example 2. Bases are the same, but I don't have log equals log. Got that 4 in the way. What in the world can I do with that 4? Caleb. Okay, I can let that 4 come over here as the exponent on that argument. So log base b of x to the 4th is log base b of 81. Now what? What can I do now? What can I do, Ryan? Okay, because it's log equals log, I can say that the arguments are equal because if I take the exponential with a base of b, b log b will cancel out on both sides. X to the 4th is 81. What do I need to do to solve a problem that says x to the 4th equals? What do I need to do now, Hope? You're on the right track. The 4th root. Almost. It's an even root. What do I have to do anytime it's an even root? Plus or minus. So from this work, x is plus or minus the 4th root of 81. And what's the 4th root of 81? So plus or minus 3. Now I have to check. Did both of those work? Neither of them work. One of them work. So if it's positive 3, this is fine. But if it's negative 3, I have a negative argument. So I need to throw out negative 3 and keep only x is 3. Anytime that there should be a root that needs to be thrown out, I want to see it written down and then a reason that you're throwing it out. And you can simply say that the argument must be positive as enough of a reason. But I want to see that plus or minus 4th root because I want to know that you remember 4th roots are plus or minuses. It's not that you forgot that you take plus or minuses when you have an x to the 4th. Are we good with example 2? Okay, example 3. Somebody think about that one and tell me which of our properties we can use. I like to get to log equals log if I can. Doesn't always work, but I like to get to log equals log if I can. I've got log minus log on the left. Is there some way I can get to where I have just one log over there? Ronald?
By the exponents, you have to put x plus 1 divided by x minus 1.
For the argument,
yeah.
We need to do that. So on the left, since we are subtracting logs, that means we are dividing the arguments. And now I have log 6 equals log 6. So now I know that the arguments are equal because I could raise both sides as powers of 6. Just one time on each side can I do that. And so now I have that problem. Next step to solve it. It's no longer a log problem. What do we need to do next as we are trying to solve this? Keith. Okay, multiply both sides by x minus 1 or take the cross product and we have 3x minus 3 equals x plus 1. Combine the x's, combine the constants, and x equals 2. Check. Is 2 plus 1 positive? Is 2 minus 1 positive? So we get to keep 2 as our answer. Okay, let's move on. Oh, this looks like the same property, right? Log minus log. So let's do that thing with dividing the arguments again. Log base 4 of x plus 3 over x. I don't have log base 4 equals log base 4. I don't have arguments I can just say are equal. So now what do I do? Getting a couple hands going up. Any others think you're getting some ideas of what we can try here? I can't just say argument equals argument. Ian, what do you think? Okay, two ways we could say that. We know we can always convert between exponential and log form. And so if I have log base of something equals, I could simply say this base to this power equals this argument. So I could simply say 4 to the 4th equals x plus 3 over x. Or, since I've got a log in there that I'm trying to get rid of, I can take the exponential on both sides. So this can be 4 to the equals 4 to the. Here, the 4 log 4 cancels out. And over there, I get 4 to the 4th. Same thing, either way of describing it. All right, what in the world is 4 to the 4th? 4 times 4 is 16 times 16. So 256 equals x plus 3 over x. And if we do our cross product again, 256x, okay, subtract x, 255x equals 3. Is this going to reduce? Yes, what's it going to reduce to? 1 over 85, and let's make sure that that gives us positive arguments. 1 over 85 plus 3, 1 over 85, so we are good with keeping x equals 1 over 85. And let's see. One more here. I've got log 45 and I've got log 45, but it isn't log 45 equals log 45. That 2/3 is in the way. What do I do to get that 2/3 out of the way? Blake, you're nodding your head. Do you have an idea? Exactly. We're going to take that number out in front and let that be the exponent on the 27. So we have log base 45 of x equals log base 45 of 27 to the 2/3. I have log 45 equals log 45, so I can set the arguments equal because I am taking the exponential, making both sides exponentials, 45 to the powers, and those will cancel out. And then 27 to the 2/3. Cubed root 27 squared equals. So x is 9. Does that make our argument positive? Is everybody comfortable with those? And let's move on to a general inverse one. This is a repeat of what you wrote down on that vocabulary page. I just wrote it with parentheses instead of the little circles. So it's still f of g of x has to be x, g of f of x has to be x. Both have to be true. So when you're asked to verify that they are inverses or not by calculating the compositions, you must do it both ways. And I need you to label which one is which so I can follow your work. So I need for you to do f of g of x. So you're going to label, that's what you're doing. So that is f of, and g of x is this 3x plus 9. So I'm going to put 3x plus 9 into the rule for f. So if I put that in for this x, change this x to 3x plus 9, I have to also change that x. So now I have 1/3 times, now that's a 3x plus 9, and then I still have the minus 3. If I distribute, I get x plus 3 minus 3, so that is x. So f of g worked. Then we do it the other way. G of f of x, and we label which one this is. G of, okay, f of x was originally 1/3 x minus 3. So now I need g of that. So I need to put 1/3 x minus 3 right in there as the argument for the g function. If I put it in there and change that x, I change this other x as well. So I have 3 times 1/3 x minus 3 plus 9, or x minus 9 plus 9, which is x. So that one also worked. Since I got x both times, I can say f and g are inverses. That they must both equal x. It does not work if they both equal 5x. It does not work if one equals x and the other one equals x squared. X for both. It's not that they equal each other. They have to both equal x. So any questions with any of that?